Why will this not focus? There we go. Whew. 2 days a week. Yeah. Thank God.
How long are the classes? 2 hours?
I think that one's 2.5 because it's 5 credits, 4 or 5 credits. Yeah.
We'll be taking it. What? We'll be taking it.
No, there's right around ashtrays. There's lots of ashtrays. There's lots of restaurants and shit. One thing that's cool, all the restaurants, most restaurants we go to, they have little buttons. That's the buttons that are so you have to, that's not waiting for us. Like, oh, I'm ready for restaurant 1. There they are. That's so awesome. I don't know why not they said we got it. It's like the most perfect thing. Then you don't have waiters wasting their time walking and sitting and shit. I got the last one. The first one was 2, so it's 2, 5 plus 3 is 8.
I like it. So start up here. We have here. I know. If I get tired, I start to sound like I'm from Boston or something.
Jersey.
Yeah.
Jersey.
It sounds like Ted Hannah.
What's the idea with number 1 here?
Add 3. Plus 3.
So these are all sequences. And very often sequences will have some rule that helps you determine what the next one in the sequence is going to be. And there's almost always, if I don't provide enough numbers, there's almost always more than one. So very often I would do this kind of problem. In Math 120, we do a lot of sequences in series. And I would create a problem and then get answers that are actually correct, but they're not what I was thinking when I put it together, because I didn't give enough numbers to begin with. So if I only gave 1 and 4, then there's obviously a lot of things that could be. That could be add 3. It could be multiply by 4. It could be square and add 3. It could be, who knows? So this one is obviously add 3 unless somebody sees something else. What about this guy? Yeah, multiply by -2. And 48, -96. And of course this one is a semi-famous one. If you don't know it, it's okay. It's sort of like being a famous tennis player and you never watch tennis. So 1 plus 1 is 2, 1 plus 2 is 3, plus 3 is 5, so this would be 8 and 13 is 21, 13 and 21, 34. Have you ever heard of that Fibonacci sequence?
Yes.
Did you bring it up earlier in the year?
I probably did because it's so kick-ass.
The very first thing we talked about was Fibonacci.
Really?
It's in the book.
He's got a better memory than I do.
Everything. You should look it up in aesthetics.
Yeah.
There you go. And they've done studies. They've done psychological studies on setting up, for example, they've even done like playing 2 frequencies that were from the sequence and 2 that weren't, and asking which ones people like better, and they almost always choose the one that's from the sequence. And it's just because a lot of nature is about building on itself. Yep.
With spirals, like for snails or plants or flowers, you'll see the Fibonacci sequence by measurement of like each swirl or
Yep.
whatever.
And that one that's often seen, and I have been guilty of this, I'll use this, but I always try to say that this is more of what's called a logarithmic spiral than it really is. It's Archimedean spiral. So it's not quite from the Fibonacci sequence, but it's close to something. Anyway, let's stick to just the general idea of sequences and series. So these are sequences. And what I can do is, for these first 2 especially, and I'm kind of going to do all 3 of these sections at once, just because I'm crazy like that.
Right.
So let's look at this one by itself for a minute. I can say that A1 is 1, A2 is 4, and I think you get the idea. I think this book does that right. Someday I'll get a book that does it right. And I'll show you what I mean in just a minute. All right, there's a much prettier way to do this. So AN, I want to figure out AN. I want to figure out a mathematical expression that would give me any term that I want. So you could just keep going. So if I say I want the 6th term, we've got it already. If I want the 10th term, you can add a few more terms here. If I want the 1,000,000th term, I don't want to do that. I'd much rather have a way to plug a billion in. So how do I get that equation that governs what, like, the third term is, the fourth term is, and so forth? Well, let's got to break this down. 4 is 1 plus 3. Amazing. Of course, 3 was the thing we identified as being the common, what's called the common difference. How far apart all of them are. So A3 is 7, which is 1 plus 6, which is 2 3s. A4 is 10, which is 1 plus 3 3s. So AN should be, now here's where everybody makes a mistake. 1 plus
N3s.
It's not N3s, unfortunately. I like it. Because the second was 1 3, the third was 2, the fourth was 3, so the end should be N minus 1. You guys kind of with me?
Uh-huh.
This is the most basic principle of mathematics, is that it searches for patterns and tries to formalize those patterns. Sequences are just the most obvious and direct example of that. So if you can't quite see what that says, if only they would have started at A0, like I was taught a million years ago, I would not have this ugly N minus 1 in there. That kind of detracts from the whole pattern. If you don't care, that's fine. So what would A100 be?
1 plus 99 times
1
3.
plus 99 times 3.
Twenty-nine.
298
297.
plus 1.
Oh, plus 1.
Because you can take this will be 3n minus 3 plus 1, so this will be 3n minus 2. That's a quicker way to do it. Triple 100 minus 2. You guys semi with me still? So I can take any sequence that looks like this, that has the same idea. This would not work that way. This works that way, of course, because it's based on addition. This is based on
Subtraction.
multiplication. This one's called an arithmetic sequence. This one's called a geometric. The arithmetic is nice. A for add, G for go multiply. Yeah.
Why is it geometric?
Say again?
Why is it geometric?
Why is it called geometric?
Yeah.
I forget. I truly forget. It's just the word they chose for it. I'm actually doing 12-2. I think I told you 12-2 and 12-3 together, along with 12-1. I think at some point in my life I knew, but I cannot remember.
Maybe it's like because it's by a different magnitude.
I think it's because of one of the first uses of the idea was something to do with geometry, but I can't offhand remember.
Probably with numbers.
Take your math history class for that.
Yeah, exactly.
Oh, God. It's something to do with the Greeks.
That's one reason why I want to do that, because then I can take a sabbatical, put the thing together, which means teach myself all the stuff that I don't know or I've forgotten, and then teach it. That would be awesome. So let's focus on this. Let's focus on arithmetic. So we got the general form for this, but even more generally, what does it work for any arithmetic sequence? We got this one for this, but now I want generally for any arithmetic sequence. So what was the one?
A.
The first one. So the one was A1. And then they have n minus 1. And what's the 3? Well, we just have to come up with a symbol that means the common difference. So it's not going to push you to D. So hearing that, we all can agree with that. That's what we'll use. Now, somebody up here said earlier, please, this is kind of a nice subject to end the semester with. Compared to what we have been doing, this is stupid easy. It's a little new. We got to get used to some of the terminology, picking out the parts that we need. But this is really nice. All right. So if I gave you this example here. Identify the parts first. What's A1?
It is 11.
11. What's D?
-5.
Good. -5.
Woohoo.
So in the nth term would be 11th plus -5. So -5 times n
-1.
And then you can clean that up if you want to. That would be 16 minus 5n. Is that cool?
Uh-huh.
That's not bad at all, right? Okay. So where it get yes.
So the D was after the bracket. How did it come before the bracket? The D, like how did it come before the bracket?
Because it's this times this. So I don't care what order you multiply in. It just looked prettier like that. So but I think the form is, which doesn't really matter, but yeah, they do the same thing in here. They always put the D at the end. Because again, that D is sort of like how big each step is. So to go from the first to the third, I've got to take 2 steps. So I start at 1 and I take 2 steps where each step is 3 big, so that the equation can be read in English. Start here and go this many steps. If you were taking statistics, maybe with me, that sounds very familiar, something we've done in there. Okay. Now here's something that's a little more interesting than that. There's a urban legend in mathematics. But it's not a phrase you hear very often. That, and this is on, I think I'm in, yeah, good. I want to make sure they actually do this. Section 12.2. There's a guy called Gauss who did a stupid amount of mathematics. He did a lot of physics. If you ever have to take physics, you'll be doing some Gauss stuff. It's also the unit of measurement for magnetic field strength, the Gauss. So he was kind of busy. Didn't have much of a, there was no TV to distract him. But supposedly, here's the urban legend. When he was in grade school, the teacher was going crazy. All the kids were yelling. So the teacher said, "Shut up, sit down. I want you." He said, "I want you to add up the numbers from 1 to 100." And he thought, that's going to keep him busy for a while. If you don't do that, you fail. Shut up, sit down. Go to your parents' bath. Horrible. So most everybody was doing 1 plus 2 is 3, plus 3 is 6, and this is what I was hoping for. So it would take them forever to do that, so they'd shut up. But Gauss said, screw this shit. I'm going to do, there's 101. There's 101. You with me? I mean, if I have to add up a list of numbers, does it matter what order I add them in? No. What's really nice about noticing that you get repeated sums. How many of those will I have? 50. There's 100. There's pairs of them, so there'll be 50. So it'll be 100 divided by 2. That many pairs of 1 plus 100. So the sum of the first 100 terms in this sequence is just going to be 50 times 101, which comes out to be itself kind of a nifty number. $50.
Done, teacher.
What's that?
He's like, I'm done.
Yeah, pretty much. And so he came up there in like 20 seconds. He said, "I'm done, teacher." "You cannot be done." So he sat down and he did the problem himself, and all the other students were like, "How?" So, just making this up. This actually is a true urban legend. I just don't know the details anymore, so I'm making up some of the details. It's a true urban legend. You gotta love that phrase. It truly is a myth. It truly is. This might have happened. We're not sure. That's the problem. We don't know. But in general, for any arithmetic sequence, what will the sum of the first n terms be? Well, where do you get that 100?
That's the total amount of terms.
N. Right? So that'll be n over 2. That's the pairs. And where was 1?
The first one.
Good. A1. And what's 100?
The last one.
So AN. So something a little more manageable. If I go back to this same sequence we've been beating up this whole time.
Is that really what it is?
Yes. Do it. For a while. Add these up. You're fond of me, kid. All right. So what if I do the first 6 of that? Let's check this and see if it looks right. If you add those up, what do you get?
1, 2, 3, 4.
20, 30,
It's 51.
51.
Right?
16,
39.
51.
10,
51.
51. Can you guys read my writing?
Yeah, sure.
Damn, that's good. After only one semester, I can read that. All right. So if we apply the rule, it should work, because that rule works for any arithmetic sequence. So if I want S6, it'll be 6 divided by 2 times the first guy plus the last guy. 3 times 18. What did I mess up? Oh, 16. I'm thinking ahead. 3 times 17. 51. Alright, so nothing amazing there. You guys with me so far? So for arithmetic, we've got this guy for sums, and for terms, I got that guy. Thankfully, they are written in your book, so you can actually read them. So let's turn our attention to geometric for a minute, and then I'll go back and clean up a few things from section 12.1, and then we'll be done. How many terms are there? Cool. So that's all. N is always the number of terms that I am looking at. Yeah.
Like this term, what is there after that?
AN. So the nth term would be that. So we're going to do the same thing for geometric. So just to kind of shortcut this a little bit, if I look at the geometric, and I look at it the same way we did earlier. A1 is 3. And what was the common thing going on here? Yeah, times -2. So A2 is -6, which is 3 times -2. A3 is 12, which is 3 times -2 times -2, which is -2 squared. So of course now I should be able to jump to AN would be 3 times -2 to the
1 minus n minus 1.
n minus 1. So it's the same thing about if only they would have started at A0. Then it would have been a nice nth power there, but you have to give and take similar. So in general, for geometric, AN is A1 times, now the letter we use for this, that's just got to represent the number that I see that's common. It's called the common ratio, because -6 divided by 3 is the same as 12 divided by -6.
Is it D? Is it pretty same like D?
Probably not for common ratio.
R.
R. That's a good idea. So D for difference, R for ratio, and of course to the n minus 1. So that's my general formula for finding the nth term in some geometric sequence. You guys semi with me? Bless you. I'm kind of debating in my head if I want to show you, but I pretty much know I want to. You see, they stopped too soon. Oh,
Yeah.
Do I trust myself? Oh yeah. Well, yeah, that's true. So I've got the terms equation. Now I need the sum. The sum of a geometric sequence. So if I look at a general geometric sequence, defined like this, if I write out the terms, they'll be like this: A1, R, A1, R squared, A1. Are you guys cool with that? Well, the first term would be A1. The second term would be A1R to the first. The third term would be A1R to the second. Oh yeah, it's an N. Yes. Cool. Libby's like, answer my question. Please. Alright, you guys with me? So the sum would be A1 plus RA1 plus R squared A1 plus forever. Right? Now here's a neat trick to figure out a nice closed form. And what I mean by closed form, does it make sense? Because this would go forever, really. If I wanted to go forever. Let's say I want to add up all this, all the way up to infinity. I want to add. That would go for a long time. Let's say I want to add it just up to n. Make this a little bit better. Up to the nth term. Here's a neat trick. So S is this. There's no question. So what if I do this? What if I take an R out of there? What do I end up in there? What do I end up with in there?
A1.
And this is the one I can do forever. That's right. I gotta remember which one I'm doing. The forever one or the only a little bit one?
R. Only a little bit.
I want to do the forever one. I want to do this one. Stay with me now. This gets interesting.
Okay. R.
Whoa.
Now watch. I was thinking that if I went to infinity, I would do what I was just doing. Let's just go up to the nth term.
Okay.
Sn is this. What's R times Sn?
A1R.
A1R. So let's do it like RA1 plus R squared A1 plus RA. Right? Is that cool? Because what's R times R to the n minus 1? I'm sorry. It'll be R to the n. Now, if any of you guys remember, I'm pretty sure I showed you a while back. Remember how I showed you they have a repeating decimal? I can't remember if I showed you this or not. How to write it as a fraction?
No.
Yes.
So 0.333 is x. If I multiply by 10, it becomes 3.33 forever. If I subtract those, the forever part goes away. Divided by that, I get x is 1/3, which is what 0.33 forever is. If I had 0.272727 forever, I'd multiply by 100, so I'd move the decimal over twice. So if I had 0.2727, right? If I multiply that by 100, I get 27.2727 forever, right? If I subtract those this way, so I get x equals 3/11ths there. So if you did 3 divided by 11 in your calculator, you get 0.272727. So that idea, and this explains why a repeating decimal is rational, because I can write it as a fraction. So I'm doing something very similar. This goes for a long time. Well, if I multiply this by r, if I multiply it by r, this stuff that keeps repeating kind of cancels out. So I end up with, if I subtract, this goes away, this goes away, this goes away, all the way to here, that goes away. and I end up with A1 plus R to the n A. And then I solve for Sn. So I can take an Sn out. Oops, this is an A1, sorry. Take an A1 out. Divide by 1 minus R. Oh, I'm sorry, this should be a minus. So it's subtracting, right? Whatever you say, Jeff. So I get that. So let me summarize that up here.
Okay.
We'll check it out. We'll see if it looks right. So what we have done so far is that for geometric, I get this guy to figure out a term, the 7th term, the 80th term, and I get this guy for the sum of the first however many terms. This one is definitely not obvious. I've got to do some really funky math just to get there, to write a more closed form for the sum. That's more of an open form because there's so many terms. So for example, if I take the one we got right here, if I take the first 5 terms, if I add them, what do I get? -3, 9, I can't in my head now, -15, 33. If you add the first 5 terms, somebody help me out. Yeah, 33. Good. If I would have went the other way, it would have been easy. You guys with me so far? Yes, ma'am.
When you say open, closed,
This is more of an open form because it's got so many terms to it. Whereas I would call this a more closed form because it's a more compact writing of it.
are they the same thing?
They are the same thing.
Oh, okay.
They're different forms of the same exact equation. This is the same thing as this. This is more open, this is more closed. I just call this more open, and actually the word open really only technically means if it goes forever. But to me, I like to think of it, since they are different forms, this is the more open form. And this is the less open form, because this one has a lot more terms than this one does.
I didn't realize it was. Okay.
Cool. And that word kind of makes sense, too. Hopefully. Maybe not just to me. So if I check this one out, we know that A1 is 3. We know that R is -2. We knew that from before. I better get, if I throw in there n equal to 5, I better get 33 or this whole thing can just get thrown away. So sum of the first 5 is A1, 1 minus R to the nth over 1 minus R. Now these cancel out. I see that right away. 1 minus -3, that goes away. -2 to the 5th, -32. Negative that is plus 32. 1 plus 32 is 33. Thank God. I didn't want to be the reason that whole swath of mathematics gets invalidated. So I wasn't. Yay! Jeff, that's a victory. But even that's not a pretty formula, but it's pretty simple to use. I'm not going to make you re-derive it. I'm just going to make you use it. Right? And it's not a big deal. It's not. You just have to identify the parts of the sequence you're working with, throw them in the right place, and put them in the calculator correctly, and you're done. It's pretty nice, yeah.
So which one is the, like, forever one, the sum of geometrical sequence?
Now the forever one, let me do that real quick. I'll do that off camera for some reason. So that goes forever.
This is not coming? This is not coming?
This is part of it too. Yeah, they won't see it. So like I was doing earlier, if you take, go with me. This gets weird. Remember, this goes forever, right? It never stops. Infinity is weird as shit. And you already know that infinity is weird. But one thing you can do, for example, if you had a hotel room with an infinite number of rooms, but you had an infinite number of guests, and you had one more guest come along, you just ask everybody to move over one, and then there's room for them. That's basically what I'm going to do right now. I take him out. Stay with me now. If I take an R out, what do I get in here?
A1
A1
plus RA1
plus RA1 plus R squared A1 forever. Well, this is already Sn. Isn't Sn equal to this?
Sure.
So I get Sn equals A1 plus Rsn. Solve for Sn. This only works if it goes forever. It has to go forever because the only way I can recover Sn here is if I have the exact same terms. If it stops somewhere, I wouldn't have the exact same terms. Maybe. But since this goes forever, I'm good. Just like that process I erased now, where I multiplied by 10, but I still had an infinite number of 3's that would cancel with the other infinite number of 3's, because I have as many of them as I need. So here if I subtract that, take that out, divide by 1 minus r, I get that. Now this is assuming that r must be, the absolute value of r must be less than 1. And if you think about it, this kind of makes sense. Now this is kind of weird. I want you to realize what this is saying. And I'm pretty sure they say this in the book, hopefully. Good. Do you see how this is an infinite addition problem? You're adding something to other things forever. So it should be strange that it's possible for it to add to a number, not to infinity. If I add 1 to itself, infinite number of times I get infinity. If I add 7 to 8 to 9 to 10, forever, that's going to be infinity. But if I add some numbers, for example, I'll give you a really easy example. If I do 0.1 plus 0.01 plus 0.001, you guys with me? A1 is 0.1, R is 0.1. Let me say this again. A1 is 0.1. What do I keep multiplying by? 0.1, which is certainly less than 1. If I add these up forever, won't I just get this? Which if you do my little trick we did earlier, you get 1/9. Which makes sense because triple this is 0.33 forever, which would be 3/9, which is 1/3. Yeah, I'm blowing your minds one by one. I love it.
0.1.
Say it.
0.1. You're blowing our minds.
Yeah, keep going forever. Yeah.
I said you're blowing our minds 0.1 by 0.1.
Thank you. I'll make sure I heard correctly. Okay. So that's only if you want the sum. I shouldn't even have in there. I should have like an infinity there or something. It's only if you want to go out forever.
So is it A1 1 minus or to the end, or is it A1 over?
This is if I want to stop. This is if I want to stop somewhere in my sequence.
Okay.
This is if I have an R that's less than or equal to 1. And I want to go forever.
Okay.
Add them up forever. I don't want to stop it.
Okay. Oh, okay.
If the case is like, if the R is not less than or greater than 1, or not equal to 1, we won't be able to do the sum.
Sorry, not equal to 1, sorry.
Well,
It's got to be less than 1.
less than 1.
So
If it's
if you're
equal to
approaching-
1 or greater, then this is going to go to infinity.
So if you're approaching 0 or approaching infinity, you can use this. But this is if you're trying to figure out.
This is if I want to stop somewhere. I only want to go out to the 5th term, to the 20th term, to the 18 billionth term. This is if I want to go forever and never stop.
Okay.
Cool. Why not?
I see.
Okay. So a couple things from the first section, and then we'll be done for today. Yes, sir.
At some point during this, are you going to show us like what you would ask on a test regarding these questions? Like,
That would make way too much sense. Yeah, I could do it right now. For this kind of thing here, I'd have to give you, well, basically, I have to give you a sequence like I just did. Let's see. this one. A1 is 4, R is 1/2. So if I want to see a few of the first few terms, A1 is 4, what's the next term? 2.
1/2, quarter.
And have you guys, did I talk about Zeno's paradox ever? I feel like I have, but maybe not. Zeno's paradox is where you have this poor guy Zeno, and he wants to get to the next town over. So somebody says to him, Zeno, you're never going to make it because you have to make it halfway. And then you have to make it halfway from there. And then you have to make it halfway from there. And then you have to make it halfway from there. You will never get there. And so I just told my professor when he told us that, I said, just tell him the town is twice as far away as it really is. So they'll go, what he thinks is halfway, and he'll be there. Yay! Solved your paradox. Next. Teacher didn't like each other. But to me, it's more interesting that he couldn't even be able to start moving. If you think about the other way around, to start moving, you'd have to move half of a foot, but they have to move half of that, half of that, half of that, half of that, half of that. He would never actually start moving. If he would have said that, then I would have been like, I got nothing. But anyway, so this will never go to 0, is what I'm trying to say eventually. Right? That's never going to go to 0. It's just going to get really stupid small. But supposedly, if I add all these up, and it goes forever, and it never gets to 0, it won't become infinitely big. It'll become a number. And why am I allowed to use this? Why am I allowed to use this? Because R is less than 1. Cool. So then I can just say this. The infinite sum would be A1 divided by 1 minus R. So 4 divided by half.
2. 2 or
8. 4 divided by half is 4 times 2. So 4 plus 2 plus 1 is 7. And then somehow the rest of the stuff becomes 1. As long as you go out forever. You guys semi with me? 1/2 plus 1/4 is 3/4. That's not quite 1. Plus 1/8 plus 1/16. It's sort of like that 0.1 plus 0.01 plus 0.001 thing. They never overlap on each other. They never make the whole number larger. Like this never ticks over. Because these are always one place down from there. This is sort of related to that. Maybe.
So you can only find the infinite if R is less than 1.
Beautiful. Even better, I can always find this. But if R is not less than 1, then this is infinity itself. Because then all the numbers are too big. They'll do what's called diverge. This converges. This converges to a number. If R was bigger than 1, it would diverge to infinity. All right. Whew. Maybe.
A1 over 1 minus 1.
Cool. All right. That's exactly the kind of problem I give you for that. And for the other one, it could be anything because there's no restriction on this guy here. This guy could be anything. I don't care what R is. I can always find the sum of a finite number of terms. But to find the sum of an infinite number of terms, I have to have a restriction on R to make it work. Otherwise, it just goes to infinity, and then it's not a very interesting question. Maybe, yes?
Let's say if in a question there's a R is like working as 2, like there's a multiplication and then addition. So
Gotcha. That's not being covered right now. So obviously, 12.2 and 12.3 only talk about 2 very specific types of sequences. What you're talking about completely messes up everything in both, but it's a very simple step, which is fine. You should be able to have any damn sequence you want. So if I start doing one like you said, like I double it, and then I add 3. And then I double it, and then I add 3. Well, then I've got to make its own little... It sounds like the math is easy enough. There should be a way to kind of write a formula that would give me the whatever term, right? That might be deceptively difficult, though, to tell you honestly. But we're just going to worry about the pure form of one and the other one.
Pure form.
Yeah. So, let me finish up a few little things from 12.1. And then I'll have said everything I wanted to say today. And basically what we've done through, the way I like to do this is these are very specific examples of sequences that we can go back now and talk about the more general for any sequence. Because the sequence does not have to be mathematical, for example. One of the simplest sequences I've seen that's not really mathematical, truly. I just gave it away. You guys were watching. What I normally get from somebody is they say, I was OTTFFS, OTTFSS. That's the most simple. In fact, I think that same person I said 147, comma, and then they said 147 forever. Prove I'm wrong. You suck. Simplest sequence, just repeat everything I've already seen. Yay. But what's really going on here? What's the first term? 1. Well, it's not 0, it's O. These are letters. One thing is O.
2.
The 2 is T.
3.
The third is T. The fourth is F. Fifth is F. Sixth is S.
7.
7, 8, 9, 10.
11.
Oh, does that mean something? I love the people the numerologists, who take some kind of translations of some old book, who knows who's translated it, and overlay it with something with little holes in it and say, it tells me that we're going to be hit by a shut up. Let's go away.
And the point of that was?
Huh?
We can just...
Oh, I don't know. Just to show you an example of a sequence that's not really based on numbers. Yeah. Are you going to see that in your homework? No. But I apparently don't care. I just wanted to show it to you. So, the thing with this now, just to make this distinction really clear, a sequence is something like this. There's a sequence. A series is when I add those terms up. Cool. Okay. And a series can be represented in a more compact way. Well, this is fine. What would the nth term for this be? It's almost too easy.
What?
4.
So it starts at 1, and you add
1.
1.
yeah, 1 for every n minus 1. Yeah. So this will be 1 plus n minus 1 is n. And that's why I said it's almost too easy. First term is 1, the second term is 2. So if I wanted to add this up to, let's say, 112, I could represent now, I want you to realize, you're not going to really understand, if you're really thinking about this, you're going to wonder, why the hell bring this symbol in? How does it really help? It does. I can call this, the symbol here means summation. Again, I have a lot of shout outs for my stats people. If you've ever taken stats or are currently taking stats, that should be something you know very well. So that's the Greek letter S. That's why we chose it to mean summation. So this would sum up n from what to what?
First line.
1 to 112.
First line, I love it. Now be more specific. From
First term.
1 to 1.
1 to 112. So it's a very compact way of writing that. You guys semi with me? You will appreciate the fact that I managed to put this into class at the end, because if you're going into calculus, remind me, who's going into calculus? Or who hopes to? All right. Not very long into your calc course, you will be using these symbols, and you will be talking about the algebra of these symbols. We're not going to be doing that now. All I need you to be able to do is rewrite a series in terms of, and this, or rewrite this in terms of a series. You guys semi with me? But in calculus, you're going to be going a lot further. This is one step away from the symbol used for calculus to do a lot of its things. So you take the letter S and you elongate it, and that's what's called an integration symbol. Oh yeah, it's in your future. Like 180 people. Okay. So if I had this, what's this calculator? Can you write that in that form?
So it's n equals 2.
16 to 1 top.
16.
You gotta be careful. Are there 16 terms up there? So be very careful.
Oh, 4. 4. N equals 2. N plus 2. 4 and 2. N equals 2.
So first off, how do we write this in terms of this here? It'd be 2 plus... Now, can you do it like this? So is this a arithmetic sequence?
Oh, no, it's not. It's
No,
just
good.
an equation.
So how can I determine each one then? What kind of sequence is this? Remember, the sequence is 2, 4, 8, 16. So I keep doubling it, right? So what's R? 2. So it's 2 times 2 to the n minus 1. Well, what's 2 times 2 to the n minus 1? 2 to the first times 2 to the n minus 1. What do you do with the powers? Add. What's 1 plus n minus 1? And so that was a long way to go for something that should have been very obvious, right? First one is 2 to the first. The second one is 2 squared. The third one is 2 to the third. So the nth one is 2 to the nth. So this will be the sum of 2 to the nth. N goes from
2.
No. N has to go from 1 to 4. Good. Because that would give you 2 to 16. You guys semi with me? So if you write your own sequence formula based on the sequence elements they gave you, it's always going to be from 1 to whatever, however many terms you've got. It has to be. Because that's the way you're going to build it. Yes, ma'am. Yeah, actually your calculator is able to handle sequences in series. I am not going to be showing that to you. But if you want to independently study up than that, you can. Because you'll notice, if you look at your calculator, remember where we went to polar and parametric and all that stuff? So if you hit that mode, you see the very last thing? Function, parametric, polar. If you hit mode, right below radian and degree, the last one is SEQ, which probably means sequence, yeah, not sequester. So if I wrote this down here, could you guys figure that out?
Sure. Let's see.
The two most commonly used variables in summation notation are n, and actually slightly more than that is I. And we use I really primarily because the name of this thing is the index. So math people, being the incredibly creative people they are, they said, let's use the first letter. In this case, no. Yeah. So all you got to do here, I mean, this is, if I'm not careful, it becomes busy work if I put too big of a range on there, but you just have to do, what's the first term?
3 squared minus 3.
3 squared minus 3?
So,
Right. So you get 3 squared minus 3 plus 4 squared minus 4 plus 5 squared minus 5 plus. All right, and then you just got to add those up. So you get 6 plus 12 plus 20 plus 30 plus 42. Yeah, 110. Is that all right? So I'm going to have very basic problems like I give you the sequence, the series. So the elements that are being added come from a sequence. Are you guys with me? But when I add those elements together, that's officially called a series now. But I can still figure out the form of how to tell the second, the third, the fourth this way. And that's what I throw in here, and the summation is the additions. So, or the other way around. I'll give you one that's already in summation form, and then I want you to actually figure it out. So it's just a bunch of plug and chug. That should not be horrible. Especially compared to some of the other stuff I have put you through. Okay. So that's all I had planned. Except for this.
oh yay, potions.
Give the answer key to the practice final.
Mr. Waller, I looked up why it's geometric and arithmetic, and they said it's because of means. So it's like
Arithmetic mean and geometric mean.
yes, and they said I guess when they came up with it way back in the day, they're dealing with rectangles and their sides, and that's really geometric. Yeah, well, we think that. That's the problem.
Once you guys go through that homework, it turns okay.
Do it again, sorry.
Once you guys score,
What I do is roughly like, if you get an 80%, I consider that to be good. Because it's roughly what I let people, when they do the homework, I let people miss a few and still give them full credit. But then if you get below that, I start to do, it would be what I would call correct mistakes. But you've already had like 3 chances at it, so I call that like half credit. And then if you get way too many wrong, I call that no credit. So it's really just 3 levels, just like for the stuff people turn in.
What happened there, Bill?
No credit, half credit, full credit. But I give you about, I don't know, 70 or 80% is where before I start mixing in half credit. Does that make sense? You don't have to get 100 to have perfect homework. You get an 80 on all your homeworks, you would have 100 homework score. Okay.
I'm missing some sections.
I give you some
Should I
leeway.
send you an email to unlock these sections for me?
Well, yeah. There's an official way to do it through WebAssign where I can just grant the request. So you should be able to send an extension request. And it's really easy for me. I can just grant it and then boom.
Oh, so from the same page I can send you.
Yeah, there should be something, a link for send something to my instructor or extension request.
Okay.
Yeah.
Okay. Thank you.
Sure. Yes.
Does it just mean?
It just means you're somebody doing it online.
Okay.
Yeah. So you know all too well what you're missing and not yourself. Yeah. Yep.
I just had a question about this problem and why that is not 4.
Where are we at?
This one it's for the eliminating the parameter, because when you take this and plug it in for t, you divide that by 2.
But you're cubing it. You never cubed it.
What? Yeah. Oh, you have to cube the.
Because isn't there 2 inside?
Yeah.
Okay, so it should be 2 cubed 8.
Oh.
Yeah, but then you're cubing the whole thing, and I'm not sure how that 2 got into to be
Okay.
cubed. There's only 1 2.
Okay, that's what
Good,
I
good.
thought, but I wasn't totally sure. So it should be an 8 times the 2, so...
Well, and it's even, if you want to write it like this,
Uh-huh.
then to bring this in, you officially have to make it the cube root of 2. And I
Okay.
wouldn't want to do that.
Okay.
So I would just leave it over, the whole thing over 2.
Okay, I
Yeah.
okay.
But it says something more. It says I have all this for my business, but I was cast back. Most of it.
I like it. So let me see. I don't know why I did that. Please tell me that didn't happen a lot.
Okay, so it said 3.2 to 4.4, and there's 3.2, 3.3, 3.4, 3.6, 3.7, and I only did, I think, 4.1, 4.7, 4.1.
Okay.
So I did those. And then it
That
says
sucks.
7.2 to 11.3, and
Hopefully it's... Have you guys all got, like, homework that's not supposed to be missing? Or no? Good, okay. So much of sorry.
yeah,
It
and
was
then
just you.
7, I did 7.5, 8.1 to 8.2, 8.4, 10.1 to 10.8, and then I did 11.1 and 11.2.
What might have happened is I might have been looking at the wrong row when I was, because I just typed these in myself, looking at the rows. So I might have just looked at the wrong row of stuff. You know what I'm saying?
Yeah.
Hopefully that's what happened, because there's no explanation for that. Okay, cool.
Thank you.
Sure.